this session on renewables market design. Since we only have the 2 presentations, I think with 1 hour will be enough. Sandra and Lucas will have 20 minutes to make the presentation, followed by 5 minutes of questions and answers. This is actually I have the honor to be the chair of this session, and I think it's very interesting because we are going to see the presentations of 2 papers that address the problem of renewable market design from 2 different perspectives. One is from the perspective of the capacity auction, and the other one is going to be from the ancillary services. So both of them are pretty much related, and I think we are going to have very good insights, and also experiments that are currently going on in 2 different markets, like the German one and the Chilean one. Okay, so let's start with Sandra Kretschmer. Most probably I have pronounced your name awfully, but sorry. And let's begin with the market design from renewable energy auctions and analysis of alternative auction formats.
Yes, thank you very much. Thank you. So I will just share my screen. I hope you can see it all right.
Yes.
Okay, perfect. So yeah, thank you all very much for joining the session. I'm delighted to present our research on the market design for renewable energy auctions and analysis of alternative auction designs. I hope that my internet connection will be stable because there's a thunderstorm right now. So fingers crossed that not suddenly the Wi-Fi breaks down. Okay, so this is joint work together with Martin Bichler and Paul Sutterer from the TU Munich and Veronika Grimm, who is also at the Friedrich-Alexander University in Erlangen-Nuremberg. So, as you might know, since 2017, the capacities and the feed-in premiums for renewable energy sources, also renewable energy plants in Germany, are determined in auctions. And onshore wind energy is the capacity-wise largest renewable energy technology in Germany. And since 2017, so since the start of the auction system, around 10.4 gigawatt of capacity have been awarded, but only 10% of those went to southern Germany, while the majority of the awarded capacity went to the north. This contributes to the already large discrepancy between generation capacity between north and south, which makes investment into transmission lines necessary, which is very costly, and also increases the need for redispatch, network security measures, which are also very costly. So for example, in 2017, the cost for redispatch measures was almost 1.5 billion euros. In contrast, a system optimal allocation of renewable capacity, so close to demand centers, taking into account the existing grid, can generate welfare gains of up to 2.6 billion euros a year. So in order to understand why this suboptimal allocation occurs, let's look at the current German auction system. There are 4 auctions per year. There are also some special tenders, but we're not looking at these. And there are 2 types of bidders that compete in these auctions. There are what we call institutional bidders. So those are bidders that are professional plant operators or professional bidders, and so-called citizen energy cooperatives or Bürgerenergiegesellschaften, abbreviated BEG, which are small local communities or private households that want to build a wind plant in their hometown, for example. The BEGs, so the citizen cooperatives, they face less strict rules in the auction process so that they can compete with the larger institutional bidders. And the most important difference is that while the institutional bidders face a pay-as-bid auction, so they receive the feed-in premium they bid on in the first place, the BEG face a uniform price auction. So they are awarded the highest accepted ask price, so to say. The remuneration is energy related. So this means a bidder submits a bid, for example, for a wind plant with 3 megawatt capacity and states how much remuneration per kilowatt hour they would have to earn in order to at least break even within the next 20 years. And like in most other countries that have renewable energy auctions, the winning bidders then receive a sliding feed-in premium for 20 years per kilowatt hour. So this means that they get a subsidy that covers the difference between the current market price for electricity and the awarded bid price, if the market price lies below this awarded bid price. The German auction system or design has another important feature, which is the reference yield model. The goal of this reference yield model is to generate an even distribution of capacity of wind power plants across Germany. It does so by defining a reference site, and for every wind plant or wind plant project, the expected electricity generation at this reference site is calculated and then compared to the actual electricity generation that is expected at the actual site where the plant is to be built. And this comparison then yields a proportion of site quality, and then the awarded feed-in premium is adjusted according to this relative site quality. So, for example, if I want to build a wind power plant somewhere and I see that the site might have only 80% site quality, which because it's maybe less windy than the reference site. So in this case, my feed-in premium would be adjusted upwards. And if I plan to build my wind plant at a very, very windy site, which is even more windy than the reference site, my awarded feed-in premium will be adjusted downwards. But the problem is that this reference yield model does not account for other relevant aspects, like, for example, potential network congestion that might arise from the renewables expansion, load proximity, the closeness to demand centers, or the need for redispatch, which in the end leads to an inefficient allocation and remuneration because it reduces incentives to build wind power plants at efficient sites, while it also does not provide an even distribution, as we've seen in the slide before. So let's recapitulate. We have an imbalanced capacity distribution between North and South Germany. This reference yield model sets inefficient incentives, and we know that a system optimal capacity allocation can generate welfare gains of up to 2.6 billion euros a year. This leads me to our main research questions, or the aims that we had with this study. So first of all, can minor adjustments to the existing auction design lead to an improved regional distribution of generation capacity so that we have wind plants spread out more evenly across Germany or more concentrated in the south where the demand is? And how do these minor changes or adjustments affect the resulting allocation, remuneration, so the feed-in premium, and bidder diversity, which basically means the share of citizen cooperatives that are awarded a wind plant project in the auction. And we do this by simulating 4 different auction designs, which I will show you on the next slide, and comparing the results of these different auction designs with regard to allocation quality, remuneration, and bidder diversity. Okay, so here you can see the 4 auction designs that we analyzed. The national auction design is our benchmark because it implements the cost minimal outcome where all plants get built at the most efficient or most productive sites or the most windy sites and only need small subsidies. So as in the current situation, there are 4 auctions per year. A bid contains an ask price BJ and a capacity YJ for some project J. Bids are then sorted in ascending order by ask price BJ, very simple, and then bids are accepted until the tendered capacity D is reached. The winning institutional bidders then receive their ask price, so pay as bid, and the winning BEGs receive the remuneration of the highest accepted bid, so uniform price. The national REM scenario is the current status quo. It works just like the national design, but with the difference that now bidders place bids as if they were to build their wind plant at the reference site. And then afterwards, the remuneration, so the feed-in payment they receive, is adjusted according to the site quality. In the regional design, we analyze individual auctions for each of the 16 German states. So with one auction per state per year, because otherwise the auction volume would be very small with 4 auctions per state per year. All of these 16 regional auctions are conducted simultaneously, and in each state also the system optimal capacity to be built, which we saw in the first slide, is tendered. Within each region, it's the same as the national auction design, so the most productive and wind efficient sites, so to say, are chosen first. And then also the allocation and pricing procedure is identical to the national design. But the design we're most interested in is the combinatorial design. As in the regional design, the target capacities in each region are set according to the system optimal allocation, but they are auctioned off in one single nationwide auction. So in this design, we also allow package bids, which means that bidders can place a bid on a bundle of projects at once, and bids are then awarded such that the allocation is as efficient and subsidy minimizing as possible. So by design, both the regional and the combinatorial auction design exactly implement the system optimal capacity allocation. Okay, so how do we analyze and compare these? So as I said, we conduct numerical experiments and we analyze a time frame of 1 year. So 4 auctions or 1 auction respectively for the regional and the combinatorial auction design. And we compare these 4 designs I just showed you with respect to allocation of the generation capacity, so how much capacity is built in every state, the resulting feed-in premiums, and the bidder diversity, so the share of citizen cooperatives that are successful in the auction. To calibrate our model for the experiments, we use readily available market data. So, for example, on the installed and planned onshore wind capacity in Germany, data on regional differences in site quality, so how windy it is at different sites. Also, we use information on spatially differentiated plant configurations and also investment costs for wind power plants across Germany, hourly wind power generation in kilowatt hours per kilowatt across Germany, and also the reference yield per installed kilowatt, so the expected electricity generation at the reference site for different wind power plant types. So next, let's look at our model more closely. So for all designs, we first draw an ask price, Vj, a capacity Y, and for the national REM design, also a site quality factor Q. For the national REM and the regional design, the model is basically sorting the bids in ascending order, assigning the bids to a winning set. Then the winners receive either pay as bid or uniform price, their ask price or the highest accepted ask price. Oops, what just happened? Sorry. For the combinatorial auction design, it's slightly more complicated because here we have to solve 2 problems. An allocation problem, which is we minimize weighted unit cost subject to the fact that the winning capacity has to be at least as large as the tender capacity, and subject to the fact that every project can win only once. This allocation problem, weighted unit cost, you can imagine it does that it basically makes sure that we don't choose just the cheapest project, but also a cheap project that's also sensible in a way. So if you have a very small power plant, say with a capacity of 1 kilowatt, that wants a remuneration of 5 cents per kilowatt hour, and then another project is has a capacity of 1 megawatt, but wants 1 cent per kilowatt hour. Then of course this project with the 1 megawatt is more expensive, but it also has a capacity of 1 megawatt. The other one has a capacity of 1 kilowatt. It's a lot cheaper, but it wouldn't make sense in a way to award this plant because it's so small, it has no use in a way. That's the allocation problem. And then in the second step, we solve a pricing problem, which basically means we minimize the resulting remuneration or the resulting feed-in premium payments, subject to individual rationality. So the winner's remuneration has to at least cover the winner's cost. And also to the fact that there's no envy, so that the loser's potential remuneration has to be smaller than the loser's cost, so that the losers don't have an incentive to also produce in a way. And also, of course, the feed-in premium has to be at least equal or larger than 0. Okay. So some more information on our model. The number of bidders, both institutional bidders and BEG bidders, is based on the 2018 auction data in Germany and is slightly adjusted such that the capacity requirements, both based on the network development plan, so which is the capacity expansion plan currently underlying the German auction system and aimed for by the German government, and also the capacity requirements for the system optimal allocation can be satisfied. For every auction, we consider an individual number of projects per region relative to the region's size. So at least 6 projects for the smallest state and at most 100 projects for the largest. Bidders participate in every subsequent auction unless all of their projects won in an earlier auction. Then they don't participate anymore. So we have 120 institutional bidders with 0 to 4 projects. So that means 0 to 16 per year. And if all of their 16 projects are like won already, they don't participate anymore. Then we have our treatment variables. So this means our 4 auction designs, which we change. And then as institutional bidders can place bids in multiple auctions, they can also realize synergies. So via economies of scale, if they are awarded multiple projects, either subsequently or in one single auction. There are many ways how such synergies can come into play. So we integrate 3 different synergy concepts, as we call it, and check the consistency of our results across these 3 concepts. So we have a regional synergy concept, which means that synergies arise only for wind plant projects that are realized or awarded in the same German state. Then we have cross-regional synergies, which means that synergies can be realized for projects in neighboring states. So for example, Berlin and Brandenburg, or Bavaria and Baden-Württemberg. And then we have a national synergy, which means that synergies arise for all projects across all Germany. And then we also vary the synergy level, so the intensity of these economies of scale. So for example, a synergy level of 0.2 means that a bundle of projects can cost up to 20% less than the sum of each individual project. And the more projects, the closer this cost reduction will be to the 20% or to this synergy level. Since the citizen cooperatives, so the BEGs, are small local bidders that place only one bid in a single region, they do not realize synergies. And then our outcome values, so we evaluate the outcome with respect to the average remuneration, so the average feed-in premium, allocative quality delta, so that is the share of capacity that is allocated to regions with capacity expansion or where capacity expansion is needed in the system optimal case, and eta, so the bidder diversity, which is the share of capacity that is won by citizen cooperatives. Okay, so let's take a look at our results. This table shows the outcome of the 4 auction designs with respect to our focus variables for allocative quality, bidder diversity, for no synergies, so that's the uppermost part here, and for cross-regional synergies, so synergies for neighboring states, with the levels 0.2 and 0.4. So when we look at the these last 2 columns, what we see is that an increased allocative quality, which is here indicated by a higher percentage for delta, comes at the cost of higher feed-in premium. So this is unsurprising, as not the most windy sites are chosen, but sites that are closer to demand centers, so more system optimal in a way, and those need higher subsidy payments to be profitable. As synergies increase, however, so if we move from 0 to 0.2 and from 0.2 to 0.4, the difference in the average feed-in premiums decreases, so that, for example, for a synergy level of 0.4, as you can see here, the combinatorial auction design almost has the same feed-in premium or the same price in a way as the current status quo, so the national REM, while implementing 100% the system optimal capacity allocation. And what's also important to note is that this remuneration does not, so this 5.5 cents per kilowatt hour here, does not even include the long run cost savings that would result from lower redispatch and network investment requirements when the regional target capacities from the system optimal case are implemented. So the cost for which, I said this before, were 1.5 billion a year in 2017, for example. So even though the feed-in premium might be the same, the resulting savings from the combinatorial case would make this case actually a lot cheaper in some, also in the long run. So here you can see the allocations of the 4 designs for the case in the middle of the table, so for cross-regional synergies of 0.2. And as you can see, the regional and the combinatorial auction design both exactly implement the system optimal allocation. So most of the new capacity is awarded in southern Germany, close to the demand centers, while for the other 2, so for national REM, a lot of capacity goes to states where no capacity expansion is necessary. So here in the north, and yeah, we see that the REM does work a little in that it spreads out the capacity a bit, but this is actually quite random. So lastly, looking at bidder diversity, so the last column here with eta, we see that as synergies increase, so moving from this to the second line and away to the third, we see that bidder diversity decreases, and that is because with higher synergies, institutional bidders, of course, gain a competitive advantage because they can realize the economies of scale, which the citizen cooperatives cannot. Okay, so in conclusion.
Okay.
Oh, sorry. We can see that the current auction design leads to an inefficient allocation, but a combinatorial auction design, for example, allows bidders to leverage synergies and avoid exposure risk. It also implements optimal allocation with minimal surplus cost, as we've seen, while maintaining incentives to still search and bid on the most efficient sites. It's also strategically simpler for the bidders than having to bid in a sequence of auctions, which makes it a nice candidate design for renewable energy auctions. However, this also has its limitations, because also bidder diversity can be a policy goal, and we've seen that with these synergies, and so bidder diversity decreased, but this can be implemented by adding further constraints. And also this auction design would also not be effective as long as legislative hurdles. There's, for example, a rule in one German state that limits the amount of sites that are available for wind plant projects, and judicial proceedings limit the attractiveness, so to say, of participating in the auctions at all. So thank you very much for your attention. And yeah, if you have any questions, I'm happy to take them now.
Thank you very much, Sandra, for your presentation. It has been very interesting, very clear, and very enlightening.
Yeah,
I would like to open the field for questions from the audience. Is there anyone interested in making questions? Please, go ahead. I could open a little bit, just in case people are feeling shy. I read recently that Germany is planning to open zonal pricing, to have zonal pricing. Is that related somehow? Can you relate somehow your work with this project? Because it seems like the electricity transmission from the north to the south is subject to constraints, to congestion, basically to congestion. And this is why they are thinking about this zonal pricing within Germany. So is that, can you relate somehow your results with this, with this project, this idea?
Yeah, so if there's zonal pricing, then of course the incentives would be different. So then in a way, this whole auction design would not be that necessary, because there are different prices in every region anyway for electricity. In a way, this would lead to new incentives. So then, for example, if the zones in the south would have a higher electricity price because there's less electricity available, in a way, less generation capacity, then the incentives to build wind plants there are higher. In general, but then there's also the system of the sliding feed-in premium, so which kind of negates the incentive from the zonal network, from the zonal pricing again. I don't know if Robert wants to add something to this, because he raised his hand. I'm not an expert on the zonal. I think there's also a colleague of mine here who maybe knows more about the zonal pricing. I'm not sure, so maybe he wants to add something too, but yeah.
Yes,
go ahead.
Maybe you can shed some light.
No, I was just about to ask a question, so I'm not the right person to ask about this. I can tell you the experience in Texas we have with nodal pricing, which is, I think, turns out to be really fruitful and really competitive and a really good thing in my opinion, but I don't know about zonal price. It should be implemented at one point, but
yeah,
I don't know about it.
I think with the zonal pricing, it would kind of make this whole auction system or auction design unnecessary if there were not this feed-in premium system. Because with these feed-in premium, even if the market price is higher in the south, doesn't matter, because they can still bid their ask price that they want, and this feed-in premium will kind of cover the difference. So it would make it would be cheaper for the state, for the government, with zonal pricing. But actually thinking about it now, it wouldn't change anything for the renewable power, so for the wind power plant bidders, because they are kind of independent of this, because they get these sliding feed-in premium.
Yeah, you're right. I just read in the newspapers. I don't know if you were thinking about zonal or nodal, because sometimes the newspapers, it was just a quick news. And just one more thing, because I was worried a little bit about the possibility, but you just more or less answered the question. Strategic behavior when you divide the market more and more, maybe there's a scope for strategic behavior on the part of
yeah.
institutional players. No, but you already mentioned that. So
yes, absolutely. So
yeah.
On the national basis, they are large markets, basically, these auctions. But we are aware also of the fact that strategic behavior could play a role if separate regional auctions were implemented, or if these regions get smaller and smaller, and the competition decreases dramatically. Yeah, and this would also be an additional drawback of, for example, the regional auctions, because there's not as much competition.
Okay. So if you don't have more questions, we can proceed with Lucas.
I got a question. Finally.
Sorry, Robert.
Finally, so I can.
We have time, so don't worry.
Thanks a lot for the talk. It was really interesting. I'm also working on a similar topic, but from a Texas perspective, with an eye on Germany, as I'm also from Germany. I have a question, and every time we talk about wind, somebody asked the question about solar. Did you ever think of including tenders for solar in the auction process? Because ultimately wind and solar should be treated in a similar way because they deliver the same good, which is electricity. Or would it make everything too complicated?
So we thought about this, but we then left it because currently for the solar energy auctions, there's no reference yield model. And for the solar auctions, also we have the problem that capacity is concentrated in the north. It's actually the other way around. It's more concentrated in the south. So this is actually good from a systems perspective. And it's also capacity-wise not as large and not as important in a way as the wind auctions, because they are way larger and there's a lot more electricity coming from the wind power plant. So that's why we focused on wind. But yeah, certainly this could also be extended to solar.
I was just thinking maybe it would reduce the inefficiencies of certain auction formats if you have the same auction format for wind and solar combined. And then you have, because it's more efficient in the north to have wind and more efficient in the south to have solar, and maybe the auction format would end up solving the issue and leading to a good market outcome.
I think there are also already once or twice a year auctions that are technology independent. So where all different renewable energy technologies can compete. I don't know for the latest results which technology was kind of the predominant one, but then also the problem would still remain that solar has a smaller capacity and wouldn't solve the problem that all wind plants would go to the north. I guess. I'm not sure. Yeah.
Okay. Thank you very much, Sandra, Robert, and the rest of the field. And now it's the turn of Lucas Neira, who will present the paper titled Assessing the Performance of a New Tender for Frequency Regulation Services in Chile. Go ahead.
Thanks. I'm going to share the screen.
Perfect.
Okay, great. In this presentation, we are going to talk about how the Chilean regulation related to the ancillary services has evolved during the last years, bringing to our team the opportunity to study and assess the performance of the new tender system, which was developed by the ISO for frequency regulation services in Chile. The structure of the presentation will start with a brief context of the Chilean system and the changes in regulation. Then we will define the scope of the presentation. And after that, we will explain the structure of the new tender developed by the ISO, and then analyze and assess the performance of the new tender. Finally, we will conclude the presentation with exposed topics. To start, the Chilean system is a linear system, which we usually characterize in 5 zones. From north to south, the center and the north of the system used to be a thermal system, and the center south side of the system used to be a hydrothermal system. This has changed during the last year with the integration of renewable sources across the system. The demand on the system is mostly concentrated at the center, which creates transmission challenges to transport the installed solar capacity from north to center. Chile also has commitments to reduce carbon emissions. In this way, during the first trimester of 2018, in which the renewable generation reached 12% of the system load, the emission was 9.6 million of tons. A few years later, during the first trimester of 2021, with a renewable generation reaching 20% of the system load, the emissions were reduced to 8.2 million of tons. Regarding to regulatory changes, during 2016, there was a modification in the law that established that the ISO had to design a tender for ancillary services. At that moment, the ancillary services were adjudicated through a optimization of energy and ancillary services, but based on audited cost. A few years later, the ISO created the new ancillary services tender structure and defined that the secondary and tertiary frequency controls were competitive. In this way, the ancillary services tender started to operate in 2020 and consisted in a optimization between audited costs for energy but bid-based costs for ancillary services. Due to changes on operational dynamics and costs perceived by clients and generators, the ISO reassessed the competitiveness of the market and established that it will suspend the tender since September 2020. The ancillary services tender was stopped until the beginning of 2021, returning to a optimization with audited cost, but with few differences with respect to the first phase, principally on the day-ahead program model. Finally, the ISO modified the previous proposed ancillary services tender, removing some costs from the tender, like the opportunity cost of the reserve provision. This last tender structure was declared competitive and started to operate at the beginning of 2021 until today. To understand the scope of the study, we contextualize the impact of the ancillary services on system costs. If we divided the system cost in 5 simple categories, we can obtain that there are costs related to transmission, to energy, to capacity, to site payments, and some minor costs to administrative things. When changing the structure of the ancillary services application, we mainly impact on marginal price, affecting the energy cost and the site payment cost. As an example of the impact on site payment cost, if we adjudicate units at a higher variable cost than the marginal cost, then the differences needs to be covered as a site payment. When creating an ancillary services market, an important question is, how will this mean a greater or lower cost to the system? But also, another question is if the new regulation will be in line with the dynamics of the market, especially when mid-term contracts are involved in the process. For example, some supply contracts that does not expect those variations on site payments. The answers to this question are not easy because we can compare system cost of different years and assess with that if the new tender is efficient or not. What we did in this study is an analysis of the different ancillary services structure implemented by the ISO during those years, and the consequences of them on the operational dynamics and in the cost of the system. Next, we are going to explain the different structures that the ISO implemented to adjudicate ancillary services during this year. As we identify in the regulation context, we can identify 4 phases, each one representing a different ancillary services structure. The first phase was previous the proposed tender and is characterized by that all costs are related to ancillary services are audited, but not all of them are modeled in the day-ahead program, particularly the activation costs are not. The second phase is the first one with the ancillary services tender, in which all costs related to the frequency control were included in the tender and modeled through those costs in the day-ahead program. The third phase was implemented when the ancillary services standards was stopped. Similarly to the first phase, all costs was related to the frequency control were audited, but in this case, the ISO also incorporate an estimation of the activation cost in the model of the day-ahead program. Finally, in the fourth phase, represents when the ancillary services standards came back, but in this case, a lot of the costs that were considered as part of the tender in the second phase are now audited. In this phase, the ISO established that the tender will only consider wear cost of the units. The additional cost, this additional cost could also be accounted as a non-fuel cost and should be carefully reviewed so it doesn't generate a double payment. Regarding the mechanism of bidding, we show in the figure at the bottom of the page a 3-day example. The green day is the one representing the real operation. The bidding period starts 2 days before the real operation and ends 13 hours before the real operation. And the best information that the units has when offering is an estimation that the ISO realized 2 days ahead in a day-ahead program. Before the structure of the biddings, Carmanis said in a paper related to the optimal pricing of the electricity, cited at the bottom of the page, that reserve market should be resolved often on a time scale roughly 1 order of magnitude longer than the time duration of reserve use. Another important factor is how those costs are paid. The regulation establishes that the ancillary services should be valorized according to their performance. We show in red the costs that are weighted with their performance factors. As we can see, not all costs related to ancillary services are adequately paid because of the obligation of their performance factors. This can be an important factor on the allocation of ancillary services with or without the tender. Now, we will show different analysis of operational dynamics and cost on the different phases of the ancillary services to understand the impact on the developed tender. First, in this slide, the first row of the slide shows how the participation of the ancillary center, how was the participation of the ancillary services. And while in the bottom row, we can see the proportion of all the allocated reserves by companies. According with ancillary services regulation, the tender can be cataloged in 3 categories. Complete, in green, if there was enough bids to cover the requirement. Partially committed, yellow, if there was not enough bids to cover the required reserves, and deserted, in red, if there was not bid at all. When there is not enough bids to cover the requirement, the ISO directly instructs the allocation of ancillary services. As we can see, when ancillary services tender start, there was a majority of complete adjudications, and reserve was allocated mostly to 2 companies. After some months, the bids began to be incomplete, but the allocation more diversified. When tenders came back on 2021, the completed adjudication was even lower, but also more diversified. This slide shows adjudicated reserves on each services, but by technology. Positive ones are the up services, and negative ones are down services. What we can see here is a clear discontinuity between each phase, which means that the ancillary services structure does affect the operation of the system. If we focus on the second phase, it's mainly adjudicated to hydro and gas resources, in which a lower adjudication to call on renewable resources. In the third and fourth phases, there is an increase on reserve adjudication to coal and biomass, mostly in the tertiary frequency control. When resources are adjudicated to give down services, there is a need to keep a minimum level of operation. If we focus on the hydro resources allocated during the second phase, it is to be expected an increase on the dispatch of hydro resources to sustain those reserves. This may lead to an anticipated depletion of the hydro resources. To analyze the ancillary services standard, we run a benchmark which compared the actual day-ahead program made by the ISO with the ancillary services standard, with an alternative day-ahead program made by inodú without the bids of the tender, as the ISO used to do in their model of the day-ahead program before the tender's definition. The day-ahead model by the ISO has a series of inputs, including the bid prices. If we take away, those bid prices, we can model the program as the ISO used to do it before the tender. The results of the analysis of the alternative program are shown here in the bottom row. As we can see, there is a lower adjudication to reserves, to resources like gas and hydrothermal and hydro resources, which means that there is a lower requirement of those resources during the operation. This slide shows the average bid prices at which each services was adjudicated. As we can see, there is a big difference between the second and the fourth phases. That's because the structure of the tender is different. In the second phase, the opportunity cost and the activation cost of the reserves were included in the bid. While in the fourth phase, those costs are not included. This is why the average bid price in the fourth phase is lower than the second phase. When we analyze the side payments of the system related to ancillary services, we can find different costs. And what we see is that since the ancillary services structure changes start, side payments increase. If we see marginal prices, there are not the cause of the differences, because during the second semester of 2020, marginal prices were similar than the ones on the second semester of 2019. Even so, there are also periods in which each side payment increase as marginal prices increase, like in the fourth phases. Cost related to tender in gray here does have a big differences between the second and the fourth phase, and that is, as we see in the previous slide, because of the decrease on the bid average price due to the changes on the tender structure. Another challenge that the ancillary services tender has is related to the decoupling of the system as renewable technologies increase to the system. Last year, on August, while ancillary services tender was operating, the system suffered a congestion from north to south here. This congestion occurred during sun hours and required solar curtailment at the north, dropping spot price to zero on that zone. There is a lot of renewable projects under development in different zones of the system, especially in the north. And the question is, if the system keeps growing at that rate, it's probable that the transmission system will not be enough to avoid the decoupling of the system. And if the system is decoupled, the operation and the ancillary services requirements change. And then there is a change on the level of competition of each subsystem. We also have seen some limitations to provide flexibility to the system when reserves are allocated through ancillary services tender. On May 2020, a reservoir unit of the system was adjudicated with almost 300 megawatts of tertiary frequency control. As we can see in this row as a line, the area indicates the real generation during the day, and the upper two rows are other reservoirs of the system. This day, a greater demand than expected was required during peak hours, and therefore the program marginal cost in dots rise to the double during the real operation in the line in different zones. If we go back to the figure of Rappel, the reservoir which was adjudicated with tertiary frequency control, we can see that this unit could not provide enough generation during the run because it needed to hold the allocated reserves. Instead, the diesel units in the fourth row had to ramp up to provide the demand and at a higher cost. Also, at the beginning of this presentation, we talked about the performance factors and how are they incorporated in the payment of ancillary services. But when to apply this factor is not the only relevant thing about it. In a system like the Chilean system, in which there is a commitment to develop a system where the security of supply is critical, even more than the economical operation, we should also be focused on identifying when a unit is performing well. We have seen that particularly in the secondary frequency control, different performances of units was cataloged as a proper performance by the ISO, even when they do not provide the requested provision. These three figures summarize the different performances seen in the system, cataloged as a proper performance by the ISO. The figure shows which is the provider reserve at each requested provision. And that's why we expected that the performance tends to be more like the line here in the left than the area in the right. And there should also be defined metrics to evaluate the time response and the persistence of the response. We have also seen the real participation of renewable units providing down frequency control with proper performance. For example, Luz del Norte, a solar unit in the north of the system, has participated on the secondary frequency control with an inverted based AGC. This figure at the top summarizes the secondary services adjudications on 3 separate days at each hour. And it shows that the solar resources are being adjudicated even in the new ancillary services standard. The participation of the unit has allowed to reduce the adjudication of down reserve of hydro resources, which is relevant especially in a dry hydrological condition. The unit also shows a proper performance. We can see a line of down frequency control services, and it was able to provide about 3/4 of the service requirement, which is a big amount of participation. There is also a standard under development for interconnection of inverted basis resources transmission system developed by the Wind and Solar Plant Interconnection Performance Working Group of the IAEE, which signals that due to the response times of inverters, renewable units can and should provide not just primary frequency control, but also fast frequency control. To finalize, we have summarized the most important lessons of the study. One is the structure of the system should be considered when designing the ancillary services market. That means to consider the transmission structure and to understand which units or technologies can provide the services. The second is the structure of the operation and dispatch programming process is also very important when designing the operation of an ancillary services market. That is, to understand when and how often will the bidding process and the operational programming take place. The third, the performance metrics are a non-relevant factor on the implementation of ancillary services market. It is necessary to correctly pay the services in order to properly incentivize the security of the system. Finally, with integration of renewable resources, it is expected a change on the dynamics of ancillary services. In one side, the structure of the system will change. There will be a different transmission challenge and probably the coupling of the systems, the congestions. There will also be a change, not just in the way that thermal resources provide ancillary services, but also the way those units operate, probably with more changes between operational states. In the other side, the capacity of inverted basis resources to participate of ancillary services will increase. There are new standards being defined on this matter, and Chile also already have some of these units providing primary and secondary frequency control. As a general thought, security considerations and the interaction with the electricity market are a key in the transition of a 100% renewable matrix, and we will need to adapt different markets, and it will lead to different markets. The lessons learned in the last 2 years in Chile market can provide important information in this regard due to its combination of audited costs and bid-based costs. That was the presentation. Thanks for the attention, and if you have any question, I can answer.
Thank you very much, Lucas, for your presentation. Wow, a lot of information. And well, I would like to open the discussion with people. If you want to make questions to Lucas, would be very welcome. Well, it's not that I have 1 or 2 questions, that I have many questions, because I am not an expert on ancillary services, and I concentrate mostly on the ahead markets and so on. So for me, ancillary services are kind of a black box, and so it's hard for me to understand. Just like a few remarks. Who can participate in these ancillary services? Anyone, any kind of technology, any company that has whatever type of technology can participate?
Every technology that has the equipment to deliver the reserves. The only market that is reserved or limited is the secondary frequency control, because it needs an AGC system, and that's a reduced group of the units of the system.
Okay, so this is like a market-based mechanism that the ISO implements, the way the capacity of generation is allocated. Seems like there is a bidding and so on. So it's like a market, some sort of market mechanism, no?
The Chilean system has all the energy market is audited. It is not a market with bids of generators. But the new thing here is that the ISO defined a market just for the ancillary services. Then one part of the market is audited for the energy, and just a little part for the reserves is a bidding process.
Okay. Okay. So I saw one of the slides, and I don't know if I am mistaken or not, but it seems like there are not that many companies, no? Technology mix is fine, but there are not that many companies, no? BD.
In Chile, there is
Company
companies that,
participation. Yes, this one, no? Like there are the C2, for instance, is like just 70% of the 60% or something like that of the company participation is just for 2 firms. So
yes,
highly concentrated. No?
That was
Doesn't have
one.
any
Chile has a lot of companies, but with when this market of reserves start to break, there was a big concentration of reserves adjudicated just to 2 companies. This is one of the weird things of this market.
Okay. Okay. Thank you. Because I could read the paper of Sandra, but I couldn't find your paper. It has a lot of information that I had to process. Okay, so thank you very much for your participation. Any questions from the audience? Okay, so I think we are done. Okay. So thank you for your participation, and it has been a pleasure to chair this session, and have a good day.
Yeah, thank you very much for chairing the session.
Okay, bye. Enjoy.
Bye.
Good evening, everyone.
Good evening. So Lucas, please, once you have the paper, could you send me the paper? Because I have colleagues in Chile who are working in Universidad Adolfo Ibáñez, and I think they can help me a little bit to understand your paper in detail, because the ancillary services, change a lot between country to country, and Spain is different from Chile and so on. So maybe I can learn something. Okay.
We can give you some material. I think that we only record the presentation. I don't know if we are developing the paper for this.
Okay. No, once you have the paper or the publication, whatever, you can let me know at this email address, okay? Because the world of ancillary services is so different from country to country that I don't know well. There are many differences, and I have colleagues in Chile that are working in electricity market in Universidad Adolfo Ibáñez, and maybe they can help me. Okay.
Okay.
Thank you.
Thank you.
Bye. Bye, Thomas. It's been a pleasure.
Thank you. So we'll close the session now.
Okay. Bye.
All right.